Hello and welcome to another video. Quick note: while this video is part of a series, it will also be my submission to the Sum 2 event. For this reason, I'm expecting some of you to be new viewers, so I'll start with a short recap on what we're trying to do and why. In the last video, we constructed this cylindrical pendulum and found that it has 2 degrees of freedom, such that we need 2 coordinates to describe the motion of the system. We decided to use 2 angles, θ1 and θ2, and we were able to derive the Lagrangian in terms of these angles. Then, after applying the corresponding Euler-Lagrange equations, we arrived at the following pair of coupled nonlinear differential equations. Here, g is the gravitational acceleration, Ls is the length of the string, Lc is the length of the cylinder, and alpha is a dimensionless constant involving the length of the cylinder and its radius, r. And as always, the dot notation signifies differentiation with respect to time. In this video we will look for an analytical solution to this system. This is done by linearizing the system through what is often called a small angle approximation. What this means is that we assume that the cylinder only makes very small oscillations about its equilibrium position, such that the angles θ1 and θ2 remain much smaller than 1 radian at all times. For starters, this ensures that the gravitational force is almost perpendicular to the trajectory of any point on the cylinder, resulting in almost no acceleration along the trajectory, such that the rates of change of θ1 and 2 can be assumed to remain much smaller than 1 radian per second throughout the entire motion. We might then assume that their squares are approximately equal to 0, such that the terms involving them vanish. Furthermore, we can expand the signs into their Taylor series and make a similar argument. Since θ1 and 2 are so small, the terms with powers greater than 1 effectively vanish, and the signs are approximately equal to the angles themselves. We can expand the cosines as well, and since the angles are very small, their difference should be of a similar magnitude, so terms with powers greater than 1 effectively disappear. And just like that, by narrowing our scope to very small oscillations, we have now obtained a perfectly linear system. And a linear system means that we get to apply the powerful tools of linear algebra. We begin by recognizing that the system can be written as a matrix equation. Let's name the matrices A and B and the coordinate vector q to make it a bit easier to see what we're dealing with. Let's also assume that A has an inverse and multiply both sides of the equation with it. On the left-hand side, A inverse times A is just the identity matrix. And on the right-hand side we get some new matrix. Let's just call this matrix C and not worry too much about what it looks like for now. It is just some constant matrix for all we care. What we're then looking for is a vector q whose second time derivative is equal to a constant matrix times that vector. This looks suspiciously much like the classic differential equation, where the second time derivative is a constant times the function itself, and the solution is proportional to the exponential function. For any oscillatory system, we would then expect the constant c to be negative, such that the argument of the exponential is complex, and we can extract a cosine or sine through Euler's formula. Of course, we're now dealing with vectors and matrices, but it seems reasonable that some sine or cosine should be involved. We could go with either one, since a sine is essentially a phase-shifted cosine and vice versa. I'm going to go with the cosine here and insert a phase constant phi just to cover all bases. The easiest way to turn this into a valid ansatz is to add some constant vector u into the mix. We can now differentiate this twice and try inserting it into our matrix equation. we see that for any non-zero solution, the cosines cancel such that we get rid of the time dependency. The equation we're now left with tells us that applying the matrix C to the vector u gives us the same result as if we multiply u by a constant. In other words, this is an eigenvalue problem, where negative omega squared acts as an eigenvalue of the matrix C, and u is the corresponding eigenvector. As such, finding solutions to our original problem amounts to finding the eigenvalues and eigenvectors of C. We start with the eigenvalues, which means that we move both terms to the same side, insert an identity matrix, and factor out u. This now says that the matrix on the left maps any vector on the line spanned by u to the zero vector. It essentially transforms a line into a point and we lose dimensional information. The only way this is possible is if the columns of the matrix are linearly dependent, which in turn means that its determinant has to vanish, and we obtain the characteristic equation. We won't get any further now without actually computing C, so let's get started on that by multiplying B with the inverse of A. Fortunately, there is a simple formula for the inverse of a 2x2 matrix, which says to take its adjoint and divide by its determinant. This allows us to quickly acquire the inverse of A. We can then simplify the fraction a bit and multiply the matrices. I'm now going to take g times LC outside of the matrix and call this fraction capital omega squared, to remind us that it has the units of squared frequency, that is, 1 over seconds squared. I will also go ahead and introduce a second dimensionless constant, beta, as Ls over Lc, to clean the matrix up a bit further. We're now in a good spot to add omega squared times I to both sides. We then take the determinant of both sides, expand the right-hand side, and rearrange. We obtain a quadratic polynomial in omega squared, and the characteristic equation tells us to look for its zeros. From here we just need to apply the quadratic formula and simplify a bit. We arrive at two possible values for omega squared. I've labeled them with plus and minus subscripts to remind us of which sign is used before the radical. Since each omega corresponds to a particular eigenvalue of the C matrix, they are often called eigenfrequencies of the system. We'll find out more about their significance once we have the full solution, but first we need to determine the eigenvectors. This means that we return to our matrix equation, where I have now inserted omega plus and labeled its eigenvector as u plus. To find the components of U+, we convert the matrix equation into a system of equations. Since the columns of the matrix are linearly dependent, these two equations are equivalent, as in, they both contain the same information. This means that we can just pick the first one and easily solve for the second component of U+ in terms of the first component. I'm also going to introduce two more dimensionless constant gamma plus and minus, just to tidy things up. These are the last ones, I promise. Anyway, we now have this proportionality relation between the components of U+, which means that we have determined this eigenvector down to a constant. I will rename this constant C+ for simplicity's sake. We could repeat these exact steps for omega minus and U minus, but there is little point in going through that process, so I'll just write down the result. We can now use our eigenfrequencies and eigenvectors to form two linearly independent solutions, Q plus and Q minus. We then form the general solution by taking their sum. All that remains is to determine the c's and phi's, which can only be done by specifying some initial values for the angles and the rates of change. For example, let's say we have some initial coordinate state q of 0 and some initial velocity state q dot of 0. To make things a bit easier, let's also assume that we release the cylinder from rest, such that the initial velocity state is 0. The only way to accomplish this without dropping any terms of the solution is by setting phi1 and phi2 to multiples of pi, such that the signs vanish. Let's just set both to 0 to simplify the solution and initial position state as well. It is now straightforward to solve for C+ and C- in terms of the initial angles. We might convert this to a system and use substitution, but I'm going with the matrix method. I place the c's in a vector and combine the vectors into a matrix. I then compute the inverse of this matrix in the same way as earlier. I multiply both sides of the equation with this inverse and simplify, which yields expressions for C+ and C-. And that is pretty much it for the solution. There's been a lot of details which are easy to get lost in, so let's go over the essentials of what we did to get here. We started with a non-linear second-order system of differential equations, which describe the motion of a cylinder attached to a string in terms of two angles, θ1 and 2. We were able to linearize the system by narrowing our scope to very small values of these angles. We then converted the linear system into a matrix equation, and argued that a constant vector times a cosine would be a reasonable ansatz. This led to an eigenvalue problem, which we solved for the eigenfrequencies and eigenvectors. and we were able to write down the general solution as a combination of two independent terms. Lastly, after assuming that the cylinder is always released from rest, we have now determined the constants C+ and C- in terms of the release angles. I want to spend the rest of the video discussing how we can interpret this solution. So let's bring back the cylinder. I'll write down the physical parameters I've been using on the left. Let's also introduce a generalized coordinate space, where the axes represent θ1 and 2. This space is usually called configuration space, because a given point in it represents some particular configuration of our system. Take for example the current state, which we can use as an initial state if we ignore the fact that it may not satisfy the small angles requirement. In configuration space, our solution describes this state in terms of the eigenvectors u+ and u-. But to avoid clutter, let's instead consider the lines spanned by each of these vectors. I'll just label them with plus and minus. If we now release the cylinder, it will start oscillating according to our solution. In configuration space, we see that we have simultaneous oscillations in both the plus and minus directions. If we now increase the initial value of θ1 a bit, such that we release the cylinder a bit closer to the minus line, we get smaller oscillations in the plus direction. You can probably guess what happens if we release the cylinder on the minus line. On this line, the solution is represented entirely by the minus term, which means that we get no oscillations in the plus direction at all. As such, the angles θ1 and θ2 always remain directly proportional to one another, and both oscillate with the same eigenfrequency ω-. This mode of oscillation is known as an eigenmode of the system. As we can see, the minus eigenmode corresponds to in-phase oscillation of both angles, such that the cylinder swings back and forth in a smooth manner. We get the plus eigenmode by releasing the cylinder on the plus line. Once again, the angles remain proportional to each other and oscillate at the same frequency. But this time, they oscillate more rapidly due to the greater value of ω+. They are also completely out of phase with each other, such that the cylinder wobbles without much overall motion. This suggests that the minus eigenmode corresponds to the symmetric pendulum-like motion of the cylinder, while the plus eigenmode represents this antisymmetric wobbling. What our solution then says is that when we release the cylinder from some general position, we get some combination of these two distinct types of movement. Lastly, it is always a good idea to test the validity of a solution by considering a limiting case. For example, suppose that we let the dimensions of the cylinder approach 0, effectively approximating a point particle. First of all, this causes the plus eigendirection to align itself with the θ2 axis, which makes sense since an infinitesimally small cylinder should be able to wobble freely without disturbing the string. Secondly, if we now measure the period of an oscillation in the minus eigendirection, we find that it seems to match up nicely with the period of a regular point mass pendulum having length Ls. In other words, we have verified that if we let the size of the cylinder go to 0, the solution for θ1 seems to approach the expected result. Still within the realm of small oscillations, of course. In case anyone wants to prove this more rigorously, I'll leave it as an exercise for the viewer. This limit is not completely trivial to evaluate, so I'll provide a hint on how you might want to begin. At any rate, this more or less concludes everything I wanted to cover in this video. See you in the next one, where we'll solve the original, non-linear system numerically, to obtain solutions valid for all possible angles.